For years, interacting with AI meant operating a turn-based system. You wrote a prompt, waited for a response, and the process halted. But today, the architecture of AI is moving away from these passive requests toward continuous, self-directing execution loops. If you map this shift, the trajectory is clear. In November 2022, ChatGPT introduced us to foundation LLMs and multi-turn prompting. By early 2025, DeepSeek demonstrated that integrated reasoning directly translated to better outcomes. Now, in January 2026, OpenClaw has achieved true operational autonomy. Operating an autonomous agent is entirely different from pinging an LLM. An LLM API is stateless. It spins up for a single task and forgets you exist. An autonomous agent, however, must hold context, analyze errors, and continuously iterate across long-running background processes. This continuous feedback loop demands an enormous amount of persistent compute. As researchers like Andrei Karpathy have noted, standard edge hardware, even clustered together, lacks the raw density to handle this load. We are going to need a lot more compute where we're going. You cannot simply outsource this problem to the cloud. Relying on remote APIs for a continuously reasoning agent introduces crippling latency. If every micro-decision requires a round trip to a distant server, the execution loop bottlenecks and the agent stalls out. Scaling AI autonomy requires solving for physical infrastructure. To maintain the necessary speed, the execution environment depends on high-density compute pushed directly to the local edge. But pushing an agent to the local edge creates a severe security problem. To be useful, an autonomous agent needs unrestricted access to local memory, functional software tools, and an active system terminal to run code. This is a stark contrast to standard cloud models. When you query a cloud LLM, the model processes text inside a heavily locked-down remote container, completely isolated from your own operating system. By giving a self-prompting, self-evolving reasoning engine direct control over a local host terminal, you are intentionally opening a direct, persistent point of entry into the host hardware. Standard application-level sandboxes are inadequate for this. They are built to contain static applications with predictable behaviors, not dynamic reasoning engines actively designing and rewriting their own execution paths to bypass obstacles. This is the core engineering tension. Providing the execution freedom required for true AI autonomy directly compromises the security of the host machine. Resolving this requires a radical redesign of the operating system architecture itself. To solve the hardware bottleneck, NVIDIA engineered the DGX Spark, a localized AI supercomputer built for the desk, establishing the foundation for autonomous execution. It is highly tower efficient, designed to run 24/7 without melting down, and holds enough VRAM to host a 200 billion parameter model entirely on local hardware. Let's examine the software layer, the OpenClaw agent. It is constructed from 3 distinct submodules: a core definition, a persistent memory bank, and base skills. These components continuously feed commands into a central execution terminal. This localized stack gives the agent the baseline horsepower and structural logic to operate continuously. However, in this default state, the agent is entirely static. It can only execute the precise skills it was initially programmed with. If an agent is going to evolve and solve novel problems, it cannot be constrained by its base programming. It must be able to seek out and acquire new tools dynamically. This is where ClawHub comes in. It serves as an external, community-driven repository where the agent can independently discover and download new subagents and coding frameworks as it encounters tasks it doesn't already know how to solve. But look closely at how this ingestion works. The agent pulls these unverified scripts directly from ClawHub and injects them straight into its own local execution terminal. Warning tone. The threat here is severe. The system is autonomously executing completely unverified, third-party code directly inside the local host's operational space. Because continuous evolution requires importing unsecure skills, allowing the agent bare metal access to the host machine presents an unacceptable enterprise risk. The environment demands a rigorous isolation strategy. The architectural answer to this ingestion risk is the NVIDIA OpenShell Sandbox policy engine. It creates a hardened execution boundary around the agent's terminal and skills modules. Importantly, OpenShell does not rely on fragile application-level guardrails that an intelligent agent might reason its way around. Instead, it enforces strict isolation protocols deep at the Linux operating system level. This chart details how OpenShell's OS-level controls neutralize agent threats. For credential theft, Linux landlock confines the agent, blocking access to SSH keys. Against privilege escalation, seccomp filtering blocks dangerous system calls. Finally, to prevent data exfiltration, network guardrails deny unauthorized outbound traffic. By mapping these granular Linux kernel security features to the agent's dynamic execution environment, OpenShell ensures every system call and network request is validated by the host OS before execution. The sandbox secures the code execution, but the computational logic requires its own oversight. Despite operating a powerful local model, the agent will inevitably generate complex reasoning requests that demand the sheer scale of a cloud-based frontier model. This introduces the privacy router. Before leaving the sandbox, it intercepts and inspects every payload. Sensitive enterprise tasks are strictly routed downward to execute on the local DGX model, while general, non-sensitive reasoning tasks route outward to external cloud models. This layer guarantees that even as the agent autonomously seeks external compute power, the enterprise maintains absolute control over exactly where its data goes. Let's trace a secure execution loop through the stack. Tasked with a new objective, the OpenClaw agent autonomously downloads a subagent from ClawHub. Upon execution, this subagent attempts an unauthorized system call. OpenShell policies immediately halt the process. The agent recalculates, issuing an inference request with proprietary code. The privacy router flags the data, instantly forcing computation downward to the local DGX model. Throughout this complex, multi-step process of failure, self-correction, and data routing, the host operating system was entirely secure, completely isolated from the chaos inside the execution loop. Secure autonomy is not achieved by hoping the AI aligns with your intentions, or by trusting the unverified code it downloads. It is achieved by rigorously isolating the operational physics of the agent itself. The shift to agentic AI marks a clear dividing line. We have moved past the era of basic model training. We are now dealing squarely with an infrastructure and secure execution challenge. Deploying these systems effectively requires a specific architecture, high-density localized compute paired strictly with zero-trust execution boundaries. For modern enterprise, this is the non-negotiable standard. The OpenClaw architecture transforms AI into a localized, persistent operational engine, capable of executing complex code loops while maintaining the security of the enterprise network.